Now we know that the CE is also part of analytical chemistry. We use the plate theory, and we talk about the plate theory in HPLC and GC. We have this very famous classical Van Deemter's equation plot, right? So why does C have a high efficiency? So we talk about the plate height, and we establish a relationship with the velocity of this carrier gas or liquid, right? This is what the Van Deemter equation talk about. If you remember your last module in analytical chemistry, instrumental analysis, we talk about this plate height, right? This is like a imaginary. A plate height is the sum of the three factors, the three terms here, your term A plus B over U and CU here. So this A, B, C are constant. This is the plot, right? And you have done some experiment to determine the curve. Now, A is about having a multi-pathway, right, of the analyte to move, right? In a column, HPLC column is very wide, so you have different ways of dodging the stationary phase, right, and passing through. Then B is the longitudinal diffusion here. You have some subway diffusion or movement, and C is the mass transfer with the stationary phase. So if you want to lower the plate height, right, which means you have more plates, right? If you want to lower the plate height, you will increase the efficiency. So how do you do that? Recall that in CE, just because of its nature, just because the bore of the capillary is so tiny, so there's no A term, there's no multi-path, because it's just open, and there's like I won't say single path, but very minimum multi-path, so that you can assume to be 0. And there's no C term, no mass transfer, because there's no stationary phase in the middle. It's hollow. So what happens is only the B term exists, which means the possibility of longitudinal diffusion, right? And therefore, we can reduce the equation of the Van Deemter plot for CE to be just the H, the plate height to be just a B over mu, okay, or you can be the velocity. We use this interchangeably. So in the cross section of the capillary, we can see, right, there's no stationary phase in the middle here. This is really a very thickly coated this fused silica, right? In this case, we're using the 330 micrometer, right? And this is a very narrow bore, right? You might ask, how come we need to have a very thick silica, right? So this is plastic. If we do not have a silica, which is very hard like sand, it will be very brittle, it just break too easily. But I'll show you in class that it's still very brittle, but there's a difference here. In the outside, you have a glass coating, right? And of course, remember there's also the exterior layer, which we have copper to coat it, because if without the copper, it's not so malleable, okay, to form this curvature. So back to the number of theoretical plates, right, in your capillary zone electrophoresis. So after we have reduced the term here, okay, and we do a substitution, so the number of plates is just equals to the mu v over 2d here, okay. So, and you can see that, right, the resolutions of the peaks is independent of the length of the column. So what you can do is, right, you can see the applied voltage strength, okay, right, and you multiply by the length of the capillary, and then this is what you get here. So you see that what affect the plate, the number of plates, is really the what? It's not the length of the column, right? It's something else. The voltage does have the effect. So now we talk about more about this velocity coming from the electrophoresis and its mobility. So OBS is not the screen, but observed. So this observed velocity, I think we talked about just now as well, as the sum of both the electrophoresis and electroosmosis. And if we expand further, these are just some terms. Just note what is your LE, so effective length of the capillary. And remember, it's not the whole length you dip inside the inlet outlet. It is the length from the inlet that we do an injection to the detection point of the detector, right? And then migration time, right, is your TM, and then TNM is the migration time for the neutral marker that doesn't move, doesn't change. It's a reference point. So therefore, when you apply electrophoresis in experiment, you need to also measure the distance from the start meaning the inlet, and also the window, and I will show you how to do it in class. And also the total length. So you cannot just measure, okay, I'm going to have a copper capillary of a 50 cm, but then you need to measure where's the window. That's key. Maybe effective is only 42 cm. Okay, a bit more math here. What we did was, right, just do a simple substitution. We take out this L over V term, okay, from just now here. Okay, so L in this case is the total length of the capillary. We call that. Okay. Next, because right, we have this equation. So now we make the electrophoretic mobility the subject, and this is what we get. Next, so we call that, right, to find out the efficiency. When we define efficiency, is about the number of plates in the system here. So the number of plates, right, this is from the Deemter equation, from the other class. 16 bracket migration time over the peak width, measured at the peak base of the peak square. And or sometimes we can do estimations. We can use the half of the peak height, right, the width there, and then we do a square in this manner here, 5.54. So just to recap here, the W half is the peak width, measure the half peak height. You see a triangle, half of the height, measure the width, or the width, measure at the baseline here for W for the other equation. So you might ask, why we need both or one or the other? Because sometimes, right, it's not a triangle. This is not Illuminati. Okay, it may just curve out, so you don't see a very good triangle. You can't measure the peak baseline, the width, but it might be easier because the peak somewhere in the middle is already a bit more angular, so you can see that there's more consistency to measure the peak width at half peak height. Okay, so as we know that the narrower the peak, the more sensitive it is, right? So that means the longer the migration time. But of course, it's more efficient because you don't see a lot of overlapping peaks. You can separate the analyte out. Okay. Now, peak variance, sigma square, nothing new formula. It's equal to 2 dt. The t is the diffusion constant. Cm square per second. T is the time here. So then you do a substitution. Back to slide 66 here. This is what you get. Okay. According to Giddings, right, this is a scientist. So he talked about the number of plates is, right, the square of the ratio between the length of the column over the sigma. So you see that if you combine, right, the formula from the previous page and do a substitution, this is what you get. So in conclusion, you can see that the theoretical number of plates is directly proportional to the voltage, how much you apply. Okay, of course, remember, you must fit into the Ohm's law. Once it deviates after the maximum value, it doesn't apply. No more such assumption. And the number of plates is inversely proportional to the diffusion coefficient. Okay. Next thing, we have a selectivity. How do we, when we ask a person who does research using C, you say, hey, what is the selectivity of the method? It is, we use something called the alpha. Alpha is the ratio between the difference in migration time of the adjacent peak, right, for T1, T2, and T1 with reference to the marker. So marker always comes out first, earlier signal. It is T1, this T2, right? If we can see a good proportion between the difference in the the distance migration time, then you have a good resolution and selectivity. So what effects does the electroosmotic force have on the resolution? When we raise the UF, it will decrease separation time and also give rise to a higher separation frequency. But the thing is, right, if we have a lower migration time, if all the solids, right, they come up very fast, there's a chance that there's certain overlap. Okay, maybe not the tip of the signal, but then the bottom part overlap. So it's not so good because we can't resolve and see between the two peaks whether there's another peak in the middle. So therefore, we always apply the rule of the resolution as a factor to consider. Okay. So resolution, the capital R here is the difference between the two adjacent peaks you want to see in the analyte, and then we look at the width of the peaks, okay, for 1 and 2 at the base, right, average base peak because you can't assume that for the two peaks they have the same base, the width of the baseline. Okay, when you do a substitution, this is what you get from previous slide. Okay, where delta V is the difference in velocity and V average is the average velocity. So what you do is, right, this is just very math, but you do a substitution. And here, what we're doing is, right, we are just trying to combine this part and here, such that overall you have this. Okay, we're trying to combine and simplify the term here. Okay. Now, and this is only true if we approximate them to be the same, or approximate to be the same. So that means we are saying that your mu EP, right, and mu average are similar, so that this term, right, becomes similar. Okay. And of course, how do you get this? 0.177, 1 over 4. That's the square root of a half here. Try to do a multiplication. Okay. Don't worry, this is open book test and exam. You can refer to it. Please don't memorize it. Okay, and make sure you know how to just go step by step. So in conclusion, that we can achieve a higher resolution when the difference in the signal's mobility is greater. Same thing when you have a larger difference in the migration time between adjacent signals, you have a higher resolution. So what are different types of molecules that C can separate? Proteins, AA, amino acid, peptides, nucleic acids, inorganic ions, organic bases, acids, and whole cell. One multitude of analytes. So that's why C is very, very powerful. And that's why you have different systems, as we discussed in the first lecture. Now, these are some research work, right, done by Professor Lee, my seniors in the lab here, Hu Feng. So she did this changing pH. How do you affect the electrophoresis? This is something we could ask you, like, okay, look at the trend and describe what are the result in the signals. Do you see there's non-detection of some, right, or does it increase the resolution? So CE is very good for separation and the detection of multiple ion, and it's very fast analysis, less than 10 minutes. This is another co-worker, my senior, and Professor Lee. You see that, right? This is about detection of bacteria. So every bacteria, their polysaccharides are very different. So that's for it could be a fingerprint of identification of some bacteria. This is one, okay, pure bacterial signal coming from this Edward Stair Tada. And number two is your Pseudomonas aeruginosa, right? When you analyze them, see it's the same parameter. This is signal. When you combine that, you see there's no any other complexation. It's just they remain at the same migration time. Okay. And so you see that now the peaks do not overlap, and there's no other complicated complexation or what. It means that CE is very good to detect bacteria, because we know that C instrument can be miniaturized and can carry to the site of possibly, let's say, flooding region to detect whether your tap water is being compromised. You just don't send bottles of water there and say, hey, because you have flooding, your tap water is contaminated. You got to check. You have to do detection, and to do that, you need CE, something that's not too heavy and bulky but portable. So in summary, I want to just quickly go over the advantage and disadvantages of CE here. You can see a advantage. Selectivity is a good alternative to HPLC. HPLC is not that small or miniaturized compared to CE. Very easy, predictable selectivity. And very high separation efficiency. Very high number of plates you saw is about 6 figure, right? 100,000 for N. It's very small sample size required. Very fast separation. Easily automated, doing overnight. Quantification is very linear, it's proportional. Easily coupled to MS, mass spectrometry. So CMS is very popular. And there are different modes to scan your different kinds of particle, right? Talk about ions, talk about your nucleic acids, your bacteria, your proteins, etc. But of course, nothing comes for free, right? There's also some drawback. So you can't do preparatory scale separations because it's more capillary. It's just so tiny here. You can't inside do another reaction within. And what it does is, right, for low concentration and the large volume, it's very difficult. because for C you just require a very small volume, right? When you do sampling. And we have low concentration and large volume, which means that it's accurate to pinpoint a certain part of your sample. There could be also sticky compound that will adsorb to the surface because your walls are made of a very attractive silica, right? So what if it gets stuck here, then you create some kind of a jarring path. It's not longer free. There's also kind of species that's very hard to dissolve in your buffer because when you have some kind of a solid, it clogs the way, then what you scan is no longer accurate and reproducible, right? And that is the last factor here. So in summary, C is pretty good. We talk about how the electric field drive, right, the flow of the ions, right, how you achieve the sharp profile, what affects the resolution that's high. There's also something called the EOF, electroosmotic flow, right, from an inner surface. What affects the EOF, right, voltage, buffer, pH, concentration, temperature, solvent, recovery, and how do we change and modify the direction of EOF, what affects measuring of the electrophoretic velocity and mobility, peak variance of sigma square, selectivity, right, and your resolution R. So with that, I will see you next time for more detailed explanation of C. Cheers.